Okay, so now last time we were talking a bit about multivariable calculus. So this lecture will continue with that, and I'll discuss a bit about one of the major theorems in multivariable calculus, namely the inverse function theorem. But before I get to that, let's continue with our discussion of derivatives. Well, so this note that t going to p plus tv is a parameterization of the straight line passing through p in the direction v. And what we are essentially doing when I look at this, what I am doing is essentially I am restricting the function f. Remember that f was defined in an open set around p, but I am just restricting it to the straight line, at least a portion of the straight line, and then calculating seeing what values it assumes at various points of the straight line, which is what this is. So essentially I get a function of one variable t going to f of p plus tv. So that is why this derivative, what I have here, this is a function of one variable. F itself is a function on an open set in Rn, but if I regard it as a function of t, it becomes a function of one variable. That's why this is very reminiscent of the classical derivative in the one variable case. So I could easily just divide by t and take the limit. The reason why I mentioned this here is that now there is nothing special about the straight line. So given this point p and a direction v, from one point of view there is nothing special about the straight line. After all, what is the feature of the straight line? One aspect is that when t is 0, this p plus tv will be just equal to p. So in other words, this, if I regard it as a curve, then and t as a time parameter, when t is 0, I start at p, and notice that if I differentiate this curve, I will get v. So initial starting point is p and initial velocity is v. Actually in this straight line case, the velocity is v at any t. But let us just focus on two things. So here I say that straight line, note that t is a parameterization of the straight line passing through p in the direction v. If we write alpha t equals p plus tv, then alpha 0 equals p, then alpha prime 0 is equal to v. Well, there are lots of curves. So given a point and a direction, there are lots of curves which have these two properties. It starts at p and its initial velocity should be v. So here of course I am using velocity in a loose sense. I just mean the initial derivative of this curve at t equals 0. So more generally, we can consider any differentiable curve sigma, so which is defined in some very small neighborhood of 0 minus epsilon epsilon, and the image should lie inside this U, the open set on which f is defined. More generally, we can consider any differentiable curve from here to here with sigma 0 equals p, exactly the same two properties. Sigma prime 0 equals v. Now, what do I mean by differentiable curve? Well, curve by definition is a map from an interval, open interval, into whatever the target is. So, if I say curve in U, I mean all I mean is the domain of that function is an interval. And by differentiable, what I mean is that of course, we already have the notion of differentiability of a function from Rn to Rm. So, I can use that, but really I do not need to worry about that, because this is a function of one variable. Even though the target is an open set in Rn, that is not an issue. The main point is the domain is just something in R. So, this is a function of one variable. So, it's, if I look at its components, sigma 1, sigma 2, sigma n, they are all just real valued functions of one real variable. So, I just demand that they be differentiable. So, that would but it is essentially the same thing as saying that this is differentiable in the Frechet sense. So, you do not get anything new. So, alright, we can consider any differentiable curve, and then again we can ask if limit t going to 0. Now, instead of looking at f of p plus tv, I will just look at f of sigma t. We can ask if limit f of sigma t minus f of p as before divided by t exists. And if it does exist, how is this related to the direction derivative as defined earlier? So, this is directional derivative would correspond to taking, instead of sigma, an arbitrary sigma, I would end up taking this specific sigma, which is alpha t equals p plus tv. So, therefore, well, I have the following proposition. Let suppose that f is differentiable again, when I just say differentiable, I mean Frechet differentiable. So, which is the existence of a linear map, etc. Suppose that f is differentiable at p, then we have df at p so here I also should take v belongs to Rn. So, f is differentiable, then we have dfp, the derivative as a linear map acting on this vector v is the same thing as the directional derivative of f along the direction v. So, same as v of f, and which is also the same thing as this thing here, which is limit t going to 0, f of sigma t minus f of p divided by t for any sigma from minus epsilon to u with sigma 0 equals 0, sigma prime 0 equals v. Any differentiable curve for any differentiable sigma with this property. Notice that the last thing here is just, it's the same thing as derivative in the usual one variable sense, d by dt of f of f composed with sigma at t equals 0, or it's the same thing as f composed with sigma prime at 0. So in short, what this says, this is a very useful, this is going to be very helpful later on. What we are saying here is that if f is differentiable in the Frechet sense at p, then in order to calculate, there are many ways of looking at this equation here. One thing is that in order to calculate the derivative as a linear map, so what the derivative does to a vector v, I can use this, the dfp of v. One way is that it is actually equal to the directional derivative along v. But actually this is not so helpful. What is more helpful is that this last one here, namely I can take any curve, not just the straight line. I can take any curve which just has to satisfy sigma 0 equals 0, sigma prime 0 equals v. The moment I have these two conditions, all I have to do is look at f composed with sigma. This is a function, real valued function of a real variable, and then calculate the usual derivative. So sometimes one is able to find, depending on the function f, one can find an appropriate curve sigma where it becomes quite easy to see what f composed with sigma is. So that's the value of this proposition, that in order to calculate the Frechet derivative, I can use this f composed with sigma prime 0. But there is also something else here, namely the second, the middle quantity equals the last quantity here. So remember that v of f was obtained by restricting f to the straight line through, here a small change is needed here. Sigma 0 is not 0, sigma 0 is p. Right. So v of f was obtained by restricting f to the straight line through p in the direction v and then calculating the derivative. What this is saying is that it really doesn't matter if it's a straight line or not. All you need is some curve which passes through p and whose initial direction is v. So immediately it may change directions, but as long as it starts there, one is in good shape. So for instance, as an example, so let's take p. So in R2, let p equals 0, 1, v equals, let's say I have E1. So I'm looking at this picture. So this point P, is 0, 1, and perhaps I should write it on the other side, or rather below. So this is, oops, so this point P is 0, 1, and this V is 1, 0. So through this point and in this direction, of course, the straight line is what I called alpha t. Alpha t is the parameterized curve P plus TV, which is t comma 1. So I'll just get, so it's just, this is alpha t, this horizontal line. Now of course I have another natural curve which passes through this point and is tangent to V. Namely, if I can take portion of a circle here. If sigma t so I need if sigma t is the parameterization of a portion of the unit circle, with unit circle with sigma 0 equals 0, 1, sigma prime 0 equals 1, 0, then so basically these two curves, well, this sigma satisfies the hypothesis of this small proposition here. So if we have a function which is differentiable, then if f from R2 to R is differentiable at P at 0, 1, then f composed with alpha prime 0 equals f composed with sigma prime 0, and both of them are equal to df at P. So this is P. So dfp acting on E1, right, and this is also equal to df by del x1 del f by del x1 at 0, 1. Right. So as a small exercise, one can write down the explicit equations for this sigma t. So just the normal parameterization of a circle would be something like sigma t is cos t sin t. However, that it would go in the wrong direction. Moreover, at t equals 0, it will start at this point. The normal parameterization will start here rather than here. So one has to modify the cos t sin t a bit, and then one gets an equation for sigma t. All right. So that takes care of this. Now let me do something which is slightly more interesting than more interesting examples. So more examples of derivatives. So to talk about these examples, there's a couple of things I have to introduce. First is, let's look at this set. Let Mn R be the set of n cross n matrices. And let SNR be the set of n cross n symmetric matrices. Note that both of these vector spaces with the usual operation of matrix addition and multiplication by a scalar. Well, and in fact, since we know that, and any finite dimensional vector space is isomorphic, any two finite dimensional vector spaces are isomorphic as soon as they have the same dimension. So this we can easily see is isomorphic to some familiar Euclidean spaces. So our vector spaces, and we have isomorphisms, linear isomorphisms. So first is from phi from MnR to Rn squared. And what does this do? Well, if I take a matrix A, I am supposed to get a point in Rn squared. So I should have a n squared coordinates. Well, I just put the rows of A side by side. So A11, A1 n, oops, A1n, then I start with A21, A2n, and so it goes on till I have the last row an1, ann. This is the map. From given a matrix, I just put the rows of A side by side and then get an element of Rn squared. Here, of course, here Aij are the entries of A. So this, it's easy to check that this map from here to here is actually a bijective map and it's linear. So I have a linear isomorphism from here to here. So this is one map, and similarly from SNR I have a map to, well, so this time the Euclidean space dimension is going to be less than this, Rn squared. So it's, in fact, it is n into n plus 1 divided by 2. And this map, again I start with a matrix. This time the matrix A is going to be symmetric. I just, instead of laying out all the rows of A side by side, I just use the, recalling that symmetric just means that the terms above the diagonal are basically, if you reflect the terms above the diagonal along the diagonal, you get the terms below the diagonal as well. So what I do is I'll use the, write the first row. Now as for the second one, done. So at this point we'll stop, and I'll resume with this example and move on to other topics in multivariable calculus in my next lecture. So